Welcome to today's lecture. So we're going to start chapter 5. We're going to talk about probability function for continuous variables. So let's recall what we learned so far. Well, in this course, we start talking about different variables. Let x be a variable. Remember, this variable can be either just countable or discrete. Countable, like the numbers of students sitting in this class, the numbers of surgeries in 1 month, and so on. Or it can be continuous. What's the meaning of that? It means that it can take on values in between two numbers on an interval. So, an interval. So it means that we cannot count the exact numbers of values. So we're going to use a range of numbers starting from number A, stopping at number B on the number line. So this is your number line, and you're taking the range of numbers, like volume, like time, like height, weight. There you go. So far we talked about probability distribution for a discrete variable, p of x, function p of a variable x. And remember that one of the famous discrete probability distribution was for binomial experiments. Remember that in that case, when you want to visualize the graph, you had histogram with some bars adjacent to each other. So I expect you to ask, what if we have a continuous variable, like when we're talking about time or volume? So are we going to use the same function? Unfortunately not. We're going to introduce a new function for continuous random variable, especially for normal distributions. So we're going to use the same function, p of x notation. The definition of the function is different. And as I mentioned, one of the most important continuous distribution, probability distribution, is related to normal or bell-shaped distribution. The graph is going to be like this. Bell-shaped. Almost bell. Okay. Perfect. Very well. So I expect you to ask, what are the properties of that continuous distribution function for a normal distribution? Properties. You're on page 1. Remember that when we talk about collection of data, we're interested in talking about numerical characteristics like the center, standard deviation, and so on related to that data. We're interested to see where the center or typical value of the collection is. When you have a continuous random variable, mean, mode, and median of your data are exactly the same. You're lucky. If somebody asks us, what is the center of your collection? We can easily say, it's going to be the mode, or I can use mean or the median. Or a normal distribution mean is the same as mode is the same as median. Where are all of them? Remember that when we're talking about the graph, mean, mode, and median, they are all numbers on the horizontal axis. So suppose you have your bell-shaped graph. Mean is equal to mode is equal to the median. All of them are located on horizontal axis and they are exactly here. Well, it happens that since you have a graph, this guy is your probability distribution function. So as you can see, below the graph and x-axis, you have an area. This area is equal to 1. So the area below the graph of the probability distribution function is always 1 or 100%. 100% is 100 divided by 100, which is equal to 1. So we talked about the mode, mean, and median. Let us use mathematical symbol that we learned before. Suppose I'm using the mean, mu, mu. Okay, so on the horizontal axis, you can actually label these by using standard deviation and the number of units that the data are away from the mean using your sigma. So one standard deviation above the mean, mu plus sigma. One standard deviation below the mean, mu minus sigma. One standard deviation after the other one standard deviation, so you get 2 standard deviations above the mean, mu plus 2 sigma. 2 standard deviations below the mean, so we're going to subtract another sigma, mu minus 2 sigma. And finally, toward the tails of your graph, you're going to have mu plus 3 standard deviation away from the mean, and this is another tip for you. Here you get mu minus 3 sigma, mu minus 3 standard deviation is going to be covered by these 2 numbers. Okay, perfect. We can use this information to find the number of values clustered around the mean, 1 standard deviation, 2 standard deviations, or 3 standard deviations. But what do we need? We need, of course, to find the mean and also standard deviation. And remember that area below the graph is 1 or 100%. So you can just use empirical rule. Remember that you can get, for example, 68% in between 1 standard deviation away from the mean and so on. By using these numbers, you can get your percentage. By using percentage, you can get to these numbers on the horizontal axis. Well, I expect you to ask, you said it's a function. So what's the formula of that function? Okay, I'm going to give you the formula for that function, but please stay calm, don't panic. This function is actually defined this way. 1 over 2 sigma square root of 2 pi e raised to negative x minus mu squared divided by, if I'm not mistaken, it's going to be 2 sigma squared. This is the graph of this function. Well, luckily for us, we're going to use our calculator. It has a built-in continuous probability distribution function in it. So when we punch the numbers, it actually calculates the value for our probability distribution function. Okay, before we actually start using our calculator, then I'm going to talk about the table. Let us just visualize some of these bell curve graphs and try to analyze them. Find the numerical characteristic based on the graphs. So let's take a look at an example on page 2. So in this example, the question says, which normal curve has a greater mean? So which normal curve has a greater mean? And the second one asks, which normal curve has a greater standard deviation? Has a greater standard deviation. Okay, let us look at these two graphs. Let me use different colors. So this is the first one. Here we go. 12. And the second one. Let me just change this a little bit to match with the example in the notes. So we have graph 1, the first graph, and second graph, graph number 2. Well, which one has greater mean or greater center? For the graph 1, the mean of this graph is actually 12. So the mean of graph 1 is 12, and the mean of the second graph, graph 2, is 15. So as you can see, 15 is greater than 12. So the mean or the center of the second graph is larger than the mean or the center of the first graph. Well, how about standard deviation? Or how about the variability? Which one is more spread out? The variability of the first graph is much higher than the variability of the second graph. So take a look at the area below the first graph. It starts from this point and it extends to this point. It has a very huge range, opposed to the area below this graph, or the range starting from this point to this point. So standard deviation or variability, standard deviation of graph 1 is greater than standard deviation of graph 2. We don't actually need the actual numbers for standard deviation. We're just looking at these two graphs and checking the range of these two You can say that, hey, the variability of the first graph is of course much higher than the variability of the second graph. Well, let us look at another example here. We are on page 3. So in this example, the scaled test scores for the New York State grade 8 mathematics test are normally distributed. So we know that it's a normal distribution. Normal distribution. The normal curve shown below represents this distribution. What is the mean test score? And estimate the standard deviation of this normal distribution. Remember that we do not have the actual data. We only have the graph and some estimation about the grades. We also know that it's normally distributed. So we have a normal distribution. This is the graph of your normal distribution. So let's see, what do we have here? So first of all, I know you have some scaling on the horizontal axis for your x values, but let's get back to the properties of normal distribution and understand what's going on. Here in the middle, you have your mean. So if you find a middle number, you can actually have or guess your mean, the center. Then mean plus 1 standard deviation, when it is mean plus 2 standard deviation, and here near the tail we have mean plus 3 standard deviation. The same on the left hand side, mean minus 1 standard deviation, mean minus 2 standard deviations, and here on the other side, let me just move this a little bit here. I need a little bit more space, mean minus 3 standard deviation. So what would be your guess for the mean? What's the best number describing the middle number? What's your middle number? Look at the graph. What's the middle number? 675, okay. 675, that's good. How do we get 675? Okay, an estimation, thank you. 700 to 650. It's going to be in between. So the information that you have some numbers on your horizontal axis, okay? 2 numbers are given here and here. We're not sure if it's mean minus standard deviation and mean plus standard deviation, but you know that it's one of them is 650, and the other one is 700. Next number is 750. So these numbers are given to you. 600, and also you have 550, which is on the far left on your graph. And also you have 800 on the far right, 800. Okay, what you can do, you can say that, hey, since mean is the middle number, it's going to be in between these two numbers. So how can we get an estimation? We can say that, hey, I'm going to add 700 and 650 and divide by 2 to get the average of these two. $675. So let us settle with 675 as the middle number or the center. Then we start talking about finding the standard deviation. Very well. By looking at our graph, the graph is divided into 3 pieces. The very first piece is concave, and then it starts going up, concave up. So this is concave down, let's write it here. And this piece to the rest, concave up. The behavior of the graph, this piece on the left, the concave up. And these 2 points dividing the graph into 3 pieces are called inflection points. So inflection point. And inflection points. You have 2 inflection points here. So why inflection points are important for us? It happens that our inflection points are actually landing on mu plus standard deviation and mu minus standard deviation. So let me just move this a little bit up here to match out mean minus standard deviation. Let's just move this color a little bit here to match our inflection points. Okay, perfect. So mean plus 1 standard deviation and mean minus 1 standard deviation. Note that if you look at your graph, it's not exactly the same location as 650 and 700. So those are not the exact numbers. Take a look at your graph. Our graph is more precise. So by looking at the graph, as you can see, the inflection points are actually matching the numbers a little bit further away from 650 and further away from 700. So it's going to be, let's see, 710. Okay, so this number, 710. It's mean plus 1 standard deviation. So mean plus 1 standard deviation on our graph matches to 710. So what's the difference between 710 and 675? Because we are actually doing the subtraction between these two. So 710 minus 675 will actually give you 35, which is your standard deviation. So we estimate standard deviation, we also estimate the mean. Just estimation. Of course, we need more exact numbers, exact values by using a calculator and having all the data that are collected for these graphs. Well, as a statistician, you're dealing with a lot of different data. How do you interpret those data? How do you come up with a universal number and universal calculation so every statistician in different countries, in different regions, understand the report or the information that you're presenting to them? So this is our goal. Our goal is to present the data related to normal distribution in a universal language. That's where we start using z-scores. Z-value or z-score helps us to come up with that universal language so every statistician understands what's going on and how to interpret the data without having access to the original data. So z-value or z-score is defined as x, the value in the data collection, minus the mean divided by standard deviation. Statisticians usually use z-values to convert all x values in the original data set into z-scores, new numbers. Then they use a calculator, they use a software to actually interpret the information, and they share the information with the rest of the statisticians or put them in the report. You usually see z-values and z-scores in the reports of statisticians. And that's how we're going to convert our original data to z-values, z-scores, and being able to use the z-table or a calculator or a software to interpret the data. Well, here you have a normal distribution. Normal distribution. This is the graph of your normal distribution. The mean is in the middle. So I'm going to write down as, for example, x bar or mu, then x bar minus 1 standard deviation, plus x bar plus 2 standard deviation, and x bar plus 3 standard deviation. On the left-hand side, we have subtraction, x bar minus 1 standard deviation, x bar minus 2 standard deviation, and finally here you get x bar minus 3 standard deviation. Very well. So I'm going to take this graph and I'm going to convert that into a graph using z. So it's going to be exactly the same area, the same shape. The numbers on the horizontal axis, they are not in x, they're going to be in z. The center of your data was x bar. What is the z? Z is going to be 0. Why is that? Because z is equal to x bar minus mean divided by standard deviation. So x minus mean divided by standard deviation. Here you have your x equals to x bar. So z is going to be x bar minus mean divided by standard deviation. Mean minus mean, 0 divided by standard deviation, which is 0. That's how we get 0. It's a normal distribution, and here you get standard normal distribution. So the mean was x bar, your mean is now 0. Okay, what if I take x bar plus 1 standard deviation? What would be my next number? Let us calculate that. So we have x bar. Now I'm going to take x bar plus 1 standard deviation. What is my z? Z is x, which is x bar plus standard deviation minus mean divided by standard deviation. Mean minus mean is 0. You get standard deviation over standard deviation, which is equal to 1. So this number here is 1. What if I take x bar plus 2 standard deviations? What if I take x bar plus 3 standard deviations? As you guess, it's going to be 2, it's going to be 3, and on the left-hand side, you get -1, -2, and -3. So, as I mentioned, we're going to switch from a normal distribution to a standard normal distribution using z-scores. When you're using a calculator and you want to find the probability, let's see on page 4.